All right. Hello, everyone. Good morning for the US participants. Good afternoon for people joining from Europe. I hope you can all hear me loud and clear. So my name is Guy van den Broek, and I'm here to present you about our controller architecture. Actually, I'm here to set the stage for Ben, who's very eager to show you how the controller functions in practice. And my presentation will be more kind of like the theory behind it, like how does it all work? How does it all fit together? And why did we develop this in the first place? Before I get into the weeds of my presentation, some quick about me. So I'm the co-founder and CTO of DEP. I'm an electrical engineer by training. I have a PhD on DC microgrids, which I finished back in 2019, shortly before we founded DEP. And the people that know me, it's no surprise. I love software development, both front-end, back-end development, but also real-time control software, which is the subject of today's presentation. And one of the guiding principles I personally have is do not repeat yourself. I hate repeating myself, doing the same thing twice. And that also actually was a principle that led us to developing our microgrid operating system today. So let me show you, first of all, like a kind of reference use case for our DC microgrid controller. And I'm going to take you back all the way to the first project that Dusan and I did together, where we had to develop a controller. So let me switch to directenergypartners.com, to the site or design editor, and show you basically a part of the system that we build over there. So we, first of all, so here we are in the site in our design editor, where we can draw our DC microgrids. First of all, we have a connection to the grid somewhere. We had a DC bus to which we were connecting several loads, amongst which an EV charger, amongst which some lights, in order to power the lights from our DC bus, which is running at 350 volts DC. We had an intermediate DC-DC converter in there, like this. And then we had several other loads that were connected here, overall up to about 12 branches in total. So let me expand this. Right, like this. So, and these were all branches to connect various loads to. And we had solar involved. Draw that up here with an intermediate DC-DC unit for maximum power point tracking. And a battery storage system. And the battery storage system is connected to a power converter, which has 3 ports. So it has an AC port to connect to the grid being like a 480 volt AC connection, isolated from the DC side. And then on our battery side, we had like a 40 kilowatt hour battery system over there, operating at around like 400 volt nominal. And our converter itself was actually our 30C3 from company C plus T. So I can actually even link it into my design in here very easily to inherit all the specs from the backend. So it has like 3 ports, 480 volt AC up to 37 amps per phase, getting up to like 30 kilowatts on the AC side. And then 2 DC ports, one for connecting a battery, also up to 30 kilowatts, 100 to 1000 volts. And port number 3 is the exact mirror of port 2, essentially. So this was the system that we built in practice. And we had to control it at a certain point. So we were adding a controller there. I'm gonna add it over here. And that controller that had to talk to all these power converters. So it had to talk to the U7 power converter. So I'm gonna search for U7 like this. It had an Ethernet connection and it was communicating over Modbus TCP/IP like this. The controller also had a connection to the DC-DC MPPT, similar setup. Also over network, Modbus TCP/IP. Same for the EV charger. And then actually we also had digital I/O originating from that controller, because we built in pre-charge on every load branch over here. So here we added pre-charge. Here we added pre-charge contactors on all the low branches, because all of you who are familiar with DC systems know that actually when you energize a branch that's at 0 volt initially, you start from 0 volt and you have to charge all the input capacitors of these components at once. So you start from 0 volt, you add capacitor on a DC bus. So what will happen is you will have large inrush current flowing from the DC bus to get this capacitors charged. And that's what you want to avoid. So that's why you add in pre-charge over here to like lower the ramp rate of the current and like slow down the pre-charge and control that process. So this controller was also communicating with those pre-charge contactors. So these were just 24 volt auxiliary powers. So it's just digital I/O, adding it in here. Like this. I mean, you get the picture. This controller, we selected a Phoenix Contact controller, a PLC Next at AXE F2152 unit. And actually, anyone that would start developing software to control this system, meaning we want to control the DC bus voltage, we want to control how much solar output we might want to curtail. For instance, we want to control the battery charging in here. Anyone that wants to accomplish that needs to basically today start from scratch with such a controller. We switch back to the presentation. So what it typically looks like is like this. You get like with your industrial controller, you get like a integrated development environment where you have your controller setup, where you have different tabs open, where you have variables you can define, booleans, integers, strings, IP addresses. And then inside these tabs, you find like these type of function blocks. For instance, to control Modbus and to like read the voltage of a device, you will need a Modbus TCP IP driver. You need to hook it up. You need to define the read interval. You need to define which register you want to read. Then you get a value. that value you typically have to scale and apply an offset to in order to get the actual value in volts. You might end up reading like 65 to 3, and then you have to convert these bits into an actual value that you're using. You need to pay attention to which function codes the blocks has, where's the server address, Modbus TCP, Modbus RTU, all come with their particularities. And although each device lists that it's Modbus TCP IP, they all have kind of their different flavor of how they implement it and use it. Some devices, for instance, allow you to read at millisecond levels. The other ones are like, yeah, you need to respect a 200 millisecond read interval, otherwise our Modbus server will basically crash. So that's actually the mindset you're in at that point. You're dealing with registers, with function blocks, with variables, and you're developing this. But don't ask somebody to like return to this 6 months from now, because then you have to like learn everything again, study again how it originally works. And moreover, look at the file name. This is the file name that I gave back then. So it was 2021, June 20th. It was about 6 a.m. in the morning. So we had PPL underscore the date and time dot the PC works projects in here. And every time we got this to work, we save actually a new version, because you don't want to lose a version that works. Then you start making changes, and if something goes wrong, you want to get back to the previously working state. So that's how we used to develop controllers for these systems, which is like very time consuming and error prone. And then, yeah, for each device that you have to add, you have to start from 0. You have to read the Modbus address maps and check it again. So that's the way we are used to developing controls. Okay. We, adhering to the principle, do not repeat yourself, we didn't want for every project that we were doing to like copy and paste this project over and modify and customize it. This becomes a pain in the ass to manage, to keep track, to maintain, and to operate these systems. I mean, this file, where do you store it? You typically put it on a shared drive somewhere. Who has the latest version? What is the latest version of that controller? And I mean, I've been talking about Modbus registers. I'm not yet talking about I want to charge my battery, and I want to charge my battery when there's a lot of sunshine, or I want to island my DC microgrid from the AC side. You're literally condemned to think about the bits literally, instead of thinking about how the energy will flow. That's why we came up with an alternative, what we would call the way it should be. Here we have config files in JSON language. Let me zoom in to a portion of this. So for instance, that pre-charge component I showed to you in the diagram. A pre-charge component in reality is a set of 2 or 3 contactors, a main contactor that conducts the main current, and then an auxiliary contactor with a series resistance that controls the inrush current. So on startup, you're going to turn on the auxiliary contactor. It will pre-charge the cap through the series resistor. It will gradually ramp up. That's like a process of a couple hundred milliseconds at max, but it's controlled charging of the input capacitor of each device. And as soon as that pre-charge is completed, you're going to turn on the main contactor. So how can you add a pre-charge to this list of devices? You add it in here by just adding another JSON object structure. So each device you see has an ID. You can give it a custom name to make it more descriptive. The ID is typically a UUID. You assign a type, pre-charge. you can have a couple settings like what's the pre-charge period in seconds, how long should the auxiliary contactor remain on after the pre-charge has completed. And then if you want to like automatically pre-charge, as soon as your DC voltage is up, start pre-charging all your outputs. If the voltage exceeds a certain threshold, you can set that over here. So as soon as the main DC bus exceeds 300 volts, the pre-charge sequence kicks in. And then you have a minimum and a maximum voltage for safety and protection. So you want to also disable your pre-charge if your main DC bus voltage exceeds like 400 volt DC to protect your loads. So if by mistake the voltage would exceed 400 volts, then this pre-charge main contactor will also turn off in order to protect your load side from overvoltage. Some of these contactors have feedback as well to actually verify, okay, I sent a command to close them, are they effectively closed? And then we have an address map. The address map is nothing more than basically where is my digital output that controls that contactor. It's like main contactor, auxiliary contactor, and the digital output channel. 2 numbers are in there. And then you can also disable or enable a device by toggling this Boolean value. So before we had this, when we had to implement a pre-charge sequence, we had to define a function block, the IDE of the PLC. We had to copy paste that function block. We had to link it to the digital I/O in there. And these pre-charge units, actually, they come in 10s, 20, 30 units in there. So that's just one example where you have a lot of repetition in your code. And then something changes, and then you have to like deep dive into those functional block diagrams that you developed. In this approach, you just copy paste this block one by one. You adapt the values, and you basically load it into a controller. You even don't have to restart it. You don't have to like compile the code again, restart from scratch. No, you reload it. The controller OS will detect, oh, a change in my config settings happened, and it will like refresh its device states. So you can do like a soft restart instead of going through a full compile cycle, which can also take many minutes. And when you're testing and troubleshooting something in practice, that's annoying. With respect to our battery system, so in this case, we have a Savant converter in there, also communicating over Modbus TCP/IP on a particular IP address that I masked here on port 5502, slave ID. We have a control and an address map. I'll talk more about that in a second. We can set a communication interval, and we can, again, enable or disable this device. So here on the left-hand side, you get a list of all devices that are connected to your controller with their relevant settings in one place. And this file is called devices.json. This is a file that can be generated through DSide. So you draw your single line diagram, and you can generate your devices.json file from it directly. So instead of going text-based, you can directly derive that information from your single line diagram. So that's another time saver that we have in there. And it always makes sure that your control code reflects the actual state of your single line diagram. That's what we call a digital twin of your actual system. And this file, the ones that you might have already noticed, this file lives on GitHub. GitHub, a system that's well known in the software space for version control. So I can go in here and make changes, like here on top, for instance, it shows like what's the latest changes. So this change happened last year. It has a particular ID. I can go back in time. If something changes on my configuration that broke something, I can literally go back to the last working state and have full traceability about what has been changed, when it has been changed, and by who. And these files can then directly be downloaded on the controller directly. So again, an efficiency gain and a time saver. So this is where the foundation of our microgrid operating system was born. To run all those DC systems where we have custom power converter hardware, custom batteries that we need to integrate in a certain shape and form. It's built for reusability and scalability. You can easily copy paste certain segments. It's vendor agnostic. So like if, for instance, this battery system, let's say next year you want to replace that by a larger battery from the same vendor, from a different vendor, it's enough to like change this block. Your higher level operating algorithms, like when am I going to charge and discharge, will be exactly the same. So you don't have to go and modify your main logic. You can just change it over here and it will run as if the same Savant battery is in there. And we have built-in version control from day one. That application I was talking about to charge or discharge a battery. Here you see a sample of it. A sample where the power management system, which is developed in Python, by the way. Python is the language, the programming language we selected to develop the high-level application logic. Why Python? First of all, because Python comes with a very large ecosystem of packages you can use. They have packages also for control algorithms. They have packages for machine learning. They have packages for AI integration. They have packages to do like forecasting of solar PV power, all readily available in there. Secondly, we used Python because now you can also leverage the power of coding agents to develop your code in here. As Ben can witness, like if you want to write this type of code, nowadays you can do that in Visual Studio Code, and Python has like auto-completion, and you can even put a coding agent to work to write you this particular application. This is not something you can do in the traditional IDEs and in the traditional ways that industrial controllers have been programmed. So Python, the way it is, so we import the PVL package, which is the package that ships with the controller. That's the library with all the utility functions you see in here. First line here is we get like, what's the minimum voltage of our battery? That's a setting we will use further down here. And we built a very simple state machine in here. So a state machine where we start in the idle state. Then we enter our main routine, our power management system. So this is our loop that gets executed periodically. We have some push buttons in the system over here to like start, stop the system and reset it. So we're gonna first of all read the state of the push buttons. We start in state idle, and if our start button is pressed, we're gonna switch from idle to initialize. Okay, that's simple. So a couple lines of code to get that done. You notice already that like, if you want to do this in like traditional PLC code, you will need to have like a function block to like detect rising edges, because you push the button once and then it's supposed to like retain that state in there. So here this gets replaced by a couple lines of code in there. And I don't underestimate the amount of effort and time that gets wasted in controller development on these type of things. Well, actually, the thing you want to accomplish is like this button has been pressed, I want to switch state. So it should be as easy as this to implement it. Then when you're in the initialized state, we're going to send commands to our AC, DC converter. So we're going to set the charging current to the battery to 0. We're not going to enable the control yet. And then we'll set the control methods of the ports. So on the AC side, we're going to set it in grid following mode. So that means that the AC side will draw whatever power it needs that's demanded on the DC side. On the battery port, we're going to set it in constant current so that we can charge and discharge the battery in constant current. And port 3 at this point is disabled. So we're not going to use it now. This could equally be like constant voltage, 350 volt, for instance, to like energize a DC bus. But in this example, it's just a grid-connected battery, grid following on one end, and it will provide whatever power that's needed to compensate how much power we send to the battery and the losses internally of the converter. Then we can measure the battery voltage, again, one single line of code. And here we get like 400 volts, for instance. The offset, the scaling, bit encoding, little endian, big endian, combining two registers together in order to get to that value. That all happens under the hood. That's being taken care of by the operating system in there. You don't have to worry again about it. And then we're going to write basically a set point to like pre-charge. We're going to send to our pre-charge circuit, okay, this is our battery voltage, and if it exceeds a certain value, we're going to start the pre-charge sequence to connect that battery galvanically to our power converter. So you again see we don't have to implement here logic like close the auxiliary contactor. 2 seconds later, close the main contactor. 2.5 seconds later, open the auxiliary contactor again. No, this is built into the operating system. It knows, okay, pre-charge, this is the sequence that it needs to go through. These are the digital outputs I should control. And the sequence is built into the software in there. That's what an operating system should allow you to do. It's an abstraction layer between low-level logic and writing your actual application. If I were to compare it to like how we nowadays develop web applications, I mean, when we develop an application for a browser, we're also not dealing like color this pixel red and color that pixel blue and that pixel white in order to generate a certain image on the screen. No, we write HTML code, and that HTML code under the hood all the way gets converted down into the point where you get a matrix of RGB values that then get displayed on the screen. So there are a lot of abstraction layers that take care and hide a lot of the complexity behind the scenes. That's what our microgrid operating system is doing too. Okay, then if we then detect that actually a pre-charge has been completed, which means that we get voltage at our battery port, okay, then we're gonna switch to from initialize to charge. And then in the charge state, we're gonna read first of all the state of charge from our battery. And if that state of charge exceeds 95%, we're gonna switch to state idle. If not, we're gonna charge it at a particular current, and that current we then get from the set points. And this set point then you can set, for instance, in a Grafana user interface that runs on top of it. If it's a valid set point, it gets enabled in here. You enable control and it runs it. If we detect that there's a fault in the system, then we switch to state faults. We're gonna get errors and so on and so on. I left a portion out in here. So, but this logic fits onto a single screen in here. The initial scripts we built, and we built a lot of controllers before this existed, were way longer, way less maintainable without any version control. So we're bringing literally microgrid controls from the OT legacy way of doing things into the IT world today with version control, continuous integration, continuous deployment. How does that work? Brings me to the controller architecture. So we have our actual hardware, which are the power converters, the batteries, the solar MPPT converters, certain loads, certain generators, UPS systems, circuit breakers you want to control, voltage meters, current meters, energy meters, you name it, whatever. And it is all vendor agnostic. I mean, these JSON structures that you've seen, these are openly accessible, and these can support whatever hardware that you want to bring to your system. And you want to control it from the controller hardware, and ultimately you want to write a custom application like the one I've shown. You want to charge or discharge a battery. Simple example. What happens in between? So in between sits our microgrid operating system, the microgrid OS. The microgrid OS needs actually two things. It needs, on the one hand, your system configuration file, your devices.json, and your devices.json is system specific. So it has particular IP addresses of a system. It has particular devices, the way they are connected. So these live over here. So every site has a specific system configuration file. The microgrid OS is generic. That's reused across every site again and again and again. And on the other hand, we have a library of address and control maps. These are maps where we map, for instance, you can find the state of charge of this battery at this Modbus register, and you need to apply offset and scaling. You build this file once for a battery specifically. For SunSpec inverters, you can even reuse the same Modbus file for different types of inverters. So that's an address map, and then a control map lives next to it. It's a subtle distinction between the two, but the control map basically defines if I have to, for instance, control the current on a converter, I, for instance, need to set the control method, I need to set the current set point, and I need to enable that port. So that's basically 3 commands that need to be sequenced. That's logic that you embed into the control map, such that at a higher level, you can just say, charge my battery at 10 amps, and then under the hood, it will execute that sequence. So address map is registers to a generic set of control commands, like the one you've seen, control the ports port 1 current equals 10 amps, and the control maps take care of the sequences. And all of the information, all of the measurements, all of the set points are made available externally through Nets. We have a Nets API. Nets is an industry standard protocol that supports publish and subscribe, as well as request and response. So that makes it accessible towards other applications like your Python code, or another application can be like particular DEP applications that we ship with the controller. We have, for instance, the peak shaving, as we have shown, the self-consumption optimization, the islanding. These are apps that we developed for customers that actually want to have a turnkey controller. They buy the control from us with the apps and they deploy it on their own hardware. That's why we have these apps, but you're also completely free to develop your own Python code with your own custom logic in there. Or you can rely upon third-party apps, other people that have developed algorithms for the controller that you can reuse across your sites. An important point I forgot to mention is that this Nets API is actually the abstraction layer. So at the application level here, you're just controlling batteries. And whether that battery is Savant, is LG, is BYD, or whatever brand that you have there, it's vendor agnostic from this point onwards. The particular brand and the particularities with every device live in the address and control maps. What this abstraction layer also does for you, it will validate any set point that you send from your application to your actual hardware. If you apply a set point that's out of bounds of the safe operating area of your device, that will get blocked by the validation internally. So at your application level, you are also protected from making mistakes. At this point, when you send actual commands to your devices, that's where you might end up having safety issues. So that's what we prevent by built-in validation of every set point that we get from external apps. And because it is Python, and because it is also cloud connected or optionally cloud connected, as do some put it, some customers deliberately don't want to have cloud connection. They just run it on-prem standalone, not connected to external applications. But you can connect it to the cloud, and then you can, for instance, connect it to a messaging application like connected to WhatsApp's API to get like a message about, hey, your controller, your battery is down, or today you have consumed X kilowatt hours and generated Y kilowatt hours. You can just use it for alarming information purposes. You can connect it to like AI forecasting services. Like, this is my location. This is the amount of solar I have. Can you provide me with a forecast of how much solar I can expect in the next hour? You can connect it in here and use it in your internal logic. You can connect it to energy market data. What's the current price of the kilowatt hours in the wholesale markets? Just tie it in there, and on and on and on and on. Possibilities are endless. We, for instance, also have a Grafana application up there that allows you to then monitor multiple sites at once. So this is all possible, customizable to your particular needs. All right, so that concludes this part of the presentation about the controls architecture. I don't know whether we will have some time to address a couple questions, but at least I hope this was somewhat inspiring and insightful to you, and that I basically set the stage correctly and appropriately for Ben, who will be next showing you how this will all run in practice. So thanks for your attention.
Now, Heel, we do have a couple questions, and Ben is here as well. Ben, if you want to field the question, it looks like, in general, is each Python LOC generating a Modbus write or read? How often do you read or write multiple registers at one time? And does each smart controller have a now apply settings concept? Are you also supporting MQTT? And is MTLS implemented between NATS client and server? And whose CA are you using? Finally, a distributed focus controller that embraces pub sub go DEP. Ben, could you or Heel resolve that?
Let's maybe start with the first question, Matt. I think the first question, if I'm not mistaken, was about basically the period, like the write rate in between Modbus commands, and whether we send multiple Modbus commands at once in the control code. The question there is, yes, we do actually have parallel operation in there. So parallel operation where we send Modbus commands to different devices at the same time. So every device runs, I'm getting really technical over here, but that's like a dedicated thread in the controller where we run a Modbus driver for that particular device. So if you instruct multiple converters, for instance, in parallel, you have all of them connected to a dedicated battery system, then you might have converter 1, 2, and 3 operate at different charging currents. So if you actually write 3 lines of code to command these 3 converters, these 3 commands will get executed in the next cycle simultaneously. So you're not waiting for one to complete the write cycle, the next one to complete the write cycle, and the third one to complete the write cycle. No, it happens in parallel. There's multi-threading built in into this, which is also something that's being taken care of for you and that you don't have to worry about as well. Then the other question was about the cycle time, so the period and the frequency of read and writes in there. We can actually get up to basically the limit of the Phoenix Contact Controller hardware. So the Phoenix Contact Controller hardware, and to remind you about this, is the hardware we selected because this is the first hardware that had Linux real-time embedded on an industrial controller, which made it very open and flexible to adopt this type of microgrid operating system. And those controllers support cycle times down to like 1 millisecond up there. So like 1 kilohertz technically. Mostly in practice, we currently run it like more at like 10 milliseconds, 50 milliseconds. Sometimes it's adjustable. Why? Because of the different flavors of Modbus that certain of these devices support. Not every device, not every power converter that's out there supports reading Modbus TCP IP in millisecond level, leave alone the networking delays that happen. So like 1 millisecond is relatively fast for this type of communication protocol. But if we move from Modbus TCP IP, for instance, to CAN bus, then we can go in and support these type of cycle times that we can get down to like the one millisecond level. That's our hard limit, and yeah, anything in between there and like 100 milliseconds depends on the particular hardware you want to control. And then the other question I heard was related to the security of the NETS driver and the certificate authority that we use. So currently we have basically enabled the of course the authentication on the NETS driver to make it secure, and we can support certain certificate authorities, but today we don't have that set up yet in the controller, because so far we have not been basically asked for this particular use case to connect it with a certificate authority. But because we use libraries to do the NETS integration, we can set that up if that's the requirement for a particular project. But the honest answer today is that we haven't done it today yet, but I don't see any roadblocks there that we cannot support it if there's particular need. Did I miss any questions, Matt? Please help me.
We do have another question in the audience.
Okay.
Yes.
This is
Yeah, so wait, we have some mute. Can you maybe mute the computer? I'll repeat the question. So can we use a controller for load shedding and demand response functionalities? For example, when you have low battery capacity or when your battery is low state of charge and stuff. So application wise.
100%. That's a use case that's fully supported in there. So load shedding indeed let me maybe switch to these sides. So let's say indeed you want to control these contactors to indeed shut down certain non-critical loads into your system. You can perfectly do that and develop your application to make that happen in there. We even, for instance, have use cases where we took it even kind of what next level, where we implemented droop control curves, where in islanding mode, we wanted to be able to run this system so disconnected from the grid without a battery and from solar only. So only solar supplying certain of the loads. And of course, then your load needs to match exactly with how much solar you have available at that point. You don't have any more power available. It's 10 kilowatts of solar that you have available. Okay, then you can charge your EV at 10 kilowatts. If it's 15 kilowatts, you can charge at 15 kilowatts. How did we accomplish that? It's by implementing a voltage droop control on our loads that to support this mode of operation. So we reduce their power output if the voltage on the DC bus decreases. And that way we always converge towards the balance between supply and demand at that time in there. So that logic is actually also implemented on the controller. So that's load shedding plus, I would say, where we go beyond just load shedding by turning loads either on or off in there. But yeah, that's one use case of where it's perfectly suited for. You will write those applications in less than a day, without a doubt.
Okay, thank you. Okay, I think that was it for this session. I know we were supposed to start at 10:30. It's 10:30 now. I suppose we take a 5-minute break as well, and then we'll resume in 5 minutes with the first hands-on lab about the controller setup and configuration. So see you guys in 5 minutes. Thank you.
Great, thank you.